So we're going over the notes, and we're just adding some things in that can help with the test and help clarify some points. So we're going over the kinetic theory of matter, which describes the behavior of matter in terms of three things: the size of the particles, the motion of the particles, and the particles' energy. And we're going to start by talking about the size of the particles compared to the actual space or the volume that they're in. And we did talk yesterday or the other day about how the particles of a gas are really small compared to the volume of space that they are in. But we need to talk a little bit more about that. There are two types of gases. There are ideal gases, which are gases that we work with in this class. And then there are real gases. Now, one of the major differences between them is that the real gases, the particles are on the larger side. And so as a result of that, they actually have an attraction for each other like solids and liquids do. And an attraction for, and they have their own forces. Where we talked yesterday and we said the particles of gases have no forces. And so that is one of the big characteristics of gases. But these are ideal gases, that the particles are so small that they have no forces attached to them at all. Real gases are not like that, but we in this class don't deal with real gases. So for ideal gases, these particles are very small. And so these very small particles, they are really small compared to that volume that they're in. And that's one of the characteristics that these ideal particles have. Next, we want to talk about these collisions that I was talking about yesterday, how these particles collide with each other. We call these collisions that these particles have elastic collisions. Now, we did talk about pool balls and how the pool balls hit each other. But when that happens, not all the energy that pool ball A has, bam, is transferred into pool ball B. Does anybody know why? Pool ball A has energy, boop, and pool ball A leaves, but it doesn't take with it all of its energy. Why? Because what? No, actually, it's friction. So there's friction between the table and pool ball A, right? And even when the two balls hit, there is friction there too. And so friction takes away some of the energy that pool ball A would have to give to pool ball B. Now, when we speak about these collisions are between these very, very small particles. They are so small that friction has nothing to do with them. So they do not have friction to take away their energy. And so therefore, we can assume that these collisions have a 100% kinetic energy transfer. So this would be why balloons, the particles in the balloons, they don't eventually like slow down and turn into liquid. Because you'd think like, oh, the particles in the balloons, they're eventually going to like bang, 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 bang. And eventually they're going to lose all their energy to friction, and then they're going to slow down and they would like fall to the bottom, right? And be liquid, right? But it doesn't happen. And the reason it doesn't happen is because as they collide, there is a 100% energy transfer. So they will always maintain that energy that they have. All right? The next one is we want to define kinetic energy. So let's do that. Kinetic energy, we're going to define that just to make sure that we're all on the same page about it. Kinetic energy is the energy of being in motion. And just so we're clear, we go back to the two contributors to kinetic energy are mass and velocity. So if we're talking about a dump truck and a little tiny Fiat going the same speed, running into a brick wall, who's going to do the more damage and hit the wall with the most force, energy? That would be the dump truck. And the reason is because the mass is larger. They have the same velocity, but the mass is larger. So only mass and only velocity are contributing to that force. All right? Next. When we're talking about density, we're actually comparing gases. When we're talking about it having a low density, we're comparing gases and liquids, and we're comparing solids. And so when we do this, we know that solids have the highest density and gases have the lowest. And that's because, as we said, solids have larger particles and gases have really, really, really tiny particles that are super far apart, whereas solids have larger particles that are right next to each other. So their density is much higher. So this is density. And so when we talk about this density of gases, we talk about defining density in two ways. The first is defined as particles per volume. And the second is defined as mass per volume, which is m over v, which is equal to d for density. All right? So the lowest is gas, liquids is in the middle, and then solids have the highest density. Okay, moving on. Now, when we talk about diffusion, we talked yesterday, the other day, about the dirty diaper and the poopy diaper in the corner, and then standing in the clean corner and eventually smelling the poopy diaper. I want to be clear that this is gases moving through other gases. Moving through other gases. Now, the reason I want to clarify this is because when we talk about diffusion in biology, we're talking about particles moving through a semi-permeable membrane, but those particles are in solution. So when we're talking about particles in diffusion, the particles are moving through from a high concentration to a low concentration, just like diffusion in biology, but they're not in solution, and so their movement is through other gases. So basically, diffusion is movement from high concentration to low concentration, however that happens. Okay? Next, we're going to look at the last problem here, where we get 8.06 over 1. So I want to be clear about this 8.06 over 1, and I want to do this one more time. I want to say the rate of hydrogen over the rate of xenon is equal to 8.06 over 1. And I'm just going to put a little meters per second over here, meters per second. So we know that hydrogen is going to be faster because it's lighter and it's smaller, so we're all clear on that. That we got. And if I put the little meters per second here, that indicates faster because meters per second, right? So hydrogen travels at 8.06 meters per second. Xenon travels at 1 meter per second. So hydrogen is faster than xenon. We see that. See that? Okay, but what if I cover this up? And now I tell you that hydrogen took 8.06 seconds to get there, and xenon took 1 second to get there. Now who's faster? Hydrogen took 8.06 seconds to get there, and xenon took 1 second to get there. So now xenon is faster, right? So that's wrong, because xenon is not faster, and we know this because hydrogen is smaller and lighter. We know that hydrogen is faster. So I'm going to tell you again, can't tell you enough, I'm going to tell you again that even though you know that these units might be incorrect, putting these units here will help you to remember and remind you that this is a rate, and not a distance, all right? It has to be set against time, because if you're given a time in a problem, then the rate is the other way around. So if they say something took 20 seconds to get somewhere and something took 10 seconds to get there, they are flipped when it comes to the rate. The smaller number is now the fastest. Does that make sense? All right. All right, so now let's do the homework. Let's go over, are you period 6? Like, is my day over? Oh, God. Okay, period 6. Oh, this has been like the longest of days. Here we go. Dalton's law of partial pressures. Now, I know it was confusing because they asked for, that's not it. They asked, why can't I find anything today? I need a vacation. All right. All right. So, so they were asking for volume, but I did write in Canvas that you only have to find pressure. You don't have to find the volume. Okay, so if you didn't see that, it's okay. This is super easy. All right. Okay, so number 1, you have a sample of oxygen collected over water, which means that the water vapor and the oxygen are in the same tube. Okay? So oxygen and water, P1 and P2, oxygen and water. That's what that means. The total pressure is 760 torr. What is the pressure of the dry gas? So the dry gas is the oxygen. When you have water vapor, it's called a wet gas. So when the water vapor is in there, it's a wet gas. They want to know what the pressure is of the dry gas alone. So oxygen plus water equals 760. Water is 23.8. So I took the 760 and I subtracted the 23.8 and I get the oxygen, 736.2. Questions? Very easy. Okay? Okay, let's look at number 2. So in number 2, we have hydrogen collected over water and 750 pressure. What is the pressure, because we're not checking the volume, of the dry gas? So I take the 750 and I subtract off the water. That's it. That's all you have to do. You just need to separate the water and the dry gas. So I pulled off the water and I get 732.5. The next one, same thing, 770 torr. I subtract off the water, and that gives me 748.9. Questions? All right, let's take a look. Are there any questions? No? All right, let's take a look at number 4. Now, in problem number 4, there are 2 equations that work here, all right? equations that you want to pay attention to. The first equation that you want to pay attention to is, and I did this online if you looked at the problems, the moles of X over the total moles times the total pressure is equal to the pressure of gas X. Now, this is called the mole fraction. Basically, this is the percent, like the mole percent, but you don't multiply by 100. So it's like the number of moles over the total moles, but you don't multiply by 100, all right? So basically what this says is, if the moles are 50%, like, 50%, then the pressure is also 50%, because I can take whatever the fraction of the moles is, multiply it by the pressure, and I get the fraction of the pressure that is that element, all right? But here's the thing. You can do the same thing with the gases. See? The exact same thing. I can take the pressure fraction. Oh, sorry. The pressure fraction multiply it by the total moles, and I get the number of moles in the tank. And not only that, but the pressure fraction is equal to the mole fraction. So what does that mean? Well, if 50% of the moles, or let's say 40% of the moles are carbon dioxide, 40% of the pressure in the tank is due to carbon dioxide. If 60% of the tank is due to fluorine gas pressure, then 60% of the moles are fluorine gas. Why? Because each mole of gas exerts the same pressure on the tank no matter what gas it is. It doesn't matter what gas it is, because ideal gases are that way. It doesn't matter what gas it is. They all behave the same way because they have no interacting forces. So they have nothing that makes one particle of carbon dioxide different from a particle of hydrogen. And so because of that, whether it's a mole of hydrogen or a mole of carbon dioxide, it doesn't matter. It exerts the exact same pressure. 1 mole is 1 mole. So as a result of that, whatever the mole fraction is, it's equal to the pressure fraction. So if I have 36% hydrogen, then 36% of my moles are hydrogen, and 36% of my pressure is hydrogen. All right? Okay, let's take a look. So my first problem is, here's my mixture of moles, right? They give you the moles, and then they give you the total pressure. And they want you to find the partial pressure for each gas. So what I did, here's my partial pressure, Px, right? So what I did was I found my mole fraction, and I multiplied it times my total pressure. That's all I had to do. I just said, like, okay, so here's my mole fraction, which is my percent of the moles, times my pressure gives me the total amount of pressure for that gas. So ammonia, 3 moles, 3 of the 14. 3 of the 14 is ammonia, times the total pressure is 171. 4 of the 14 are carbon dioxide, times the total pressure, 229. 5 of the 14 moles is nitrogen, times the total pressure is 286. If I add up all of my partial pressures, I get my total pressure. Yeah. okay? The next one says, the partial pressure of fluorine in a mixture of gases where the total pressure is 1 atm is 300 torr. So the partial pressure is 1 atm. So the partial pressure is 300 torr. The total pressure is 1 atm. What is the mole fraction? So I have my partial pressure, which is 300 torr, and my total pressure, which is 1 atm. And I need to find my moles, my mole fraction. So the first thing I did was I converted my 1 atm to 760 torr. That way my 300 torr and my 1 atm are in the same unit. Then I just solved for my mole fraction. I divided my partial pressure by my total pressure, and that gave me my mole fraction. So in the case of number 5, I changed the unit to what I needed, and then I just solved. I just solved for what I needed. Question.